So in this video, we are popping back to probability now so that we can start talking about probability in the same sort of language and with the same sort of concepts as we had from data. We'll start this video with discrete probability distributions. So that is looking at random variables where the outcomes are discrete data. So a probability distribution is a function that gives probabilities to every outcome of an experiment. Notice I used the word distribution there, just like when we talked about data and I used the word distribution. We can use the same sort of languages and concepts around probability distributions as we did with data. We can start talking about its mean, its variance, its shape and its spread. So let's kick off with an example. I want the probability distribution of the outcomes of rolling a die. So rolling a die is a random variable and the outcomes are numeric data, 1, 2, 6. But each of those outcomes is discrete data. We can't have a roll of 3 1/3, for instance. There are only 6 possible values. So for a probability distribution with discrete values, we usually write down the probability distribution as just a table of probabilities. We know that the probability of getting each value of a die is equally likely. 1 to 6 are all equally likely. And because they're probabilities, they all need to add to 1. So the probability of rolling a 1 on a die must be a sixth. The probability of rolling a 2 on a die must be a sixth, and so on. And this is how we would write the probability distribution of the outcomes of rolling a die. That was quite a nice example because we could just think about what is a die and write it down, but sometimes we need to do some calculations. So in this example, I want the probability distribution of the sum of rolling 2 die. So that means we need all the possible outcomes of the sum of 2 die and the probability associated with them. So let's think about all the possible outcomes of the sum of 2 die. So we can have our first die, die number 1, or we can have our second die, die number 2. And what values can each of these take? Well, the first die can take values 1 to 6, and the second die can take values 1 to 6. So if my first die rolls a 1 and my second die rolls a 1, then what is the sum of both those die? That is 2. If my first die rolls a 2 and my second die rolls a 1, then the outcome is 3. And so on. And I can keep filling in this table. So these are all the possible outcomes we can get when we take the sum of 2 rolls of a die. Notice that each of these outcomes are equally likely. All the rolls of die 2 are equally likely. So each of these has a probability of a sixth. And each of these rolls of a die are equally likely. And they are independent events, so each of these outcomes will be equally likely also. We can check this. So we know that the second die rolling a 1 has probability a sixth, and the first die rolling a 1 has probability a sixth. Therefore, this outcome will be the probability of die 1 rolling a 1 and die 2 rolling a 1 at the same time, which is the intersection of those two outcomes. And as they're independent, we can multiply the probabilities. So a sixth multiplied by a sixth. So this outcome has probability 1 over 36. And there are 36 possible outcomes, so each of these are equally likely. So now, to find our probability distribution, we want the probability of each outcome happening. Well, some of these can happen more than once. So we just need to add up how many of them there are. So 2 happens once out of 36. 3 happens twice out of 36. 4 happens 3 times out of 36. 5, 4 times out of 36. 6, 5 times out of 36. 7, 6 times out of 36. 8, 5 times out of 36. 9, 4 times out of 36.
10 3 times out of 36, 11 2 times out of 36, and 12 once out of 36. So the possible outcomes are 2 to 12. And the probability that our random variable attains that outcome, well, 2 happens once out of 36. 3 happens twice out of 36. 4 happens 3 times out of 36, and so on. And that is our probability distribution for the sum of 2 die.
And this is the probability distribution that we have. And we call this a probability mass function, or a PMF for short. To check that we've got this right, why don't we do a Monte Carlo simulation in Excel? So I've opened up Excel and I've set up a little spreadsheet. So now I'm going to sample a value for the first die, a value for the second die. I'm going to sum them both up, and then I'm going to look at how many of each of the possible outcomes I get and what is their probability. So let's sample a value between 1 and 6 for the first die using rand between. And the same for the second die. Let's take the sum of both. And now let's run lots and lots and lots of trials. As we have so many possible outcomes, you're going to run a lot this time. So I will run 2,500 trials. So I've virtually thrown 2 die 2,500 times, and I've added up their scores. Scroll back to the start. Now, for each of my possible outcomes, I want the probability of that happening. So that's going to be how many of them are in here divided by how many trials I did, which was 2,500. So we're going to use count if this range contains the value 2. And then I want to divide by how many trials I did, which was 2,500. And I can do that for each possible outcome. So this is my estimate of the probability of each of these. Now, if I do a bar chart of this, you can see my distribution looks a bit like this sort of triangle shape. Is that what we would expect? Well, remember back to our distribution, we had the probability of, the numbers are a bit off here because of the way Excel does things, but the probability of the first value, 2, was about 1 over 36. Then the second value was double that, the third value was triple that, the fourth value was 4 times that, and so on, until we reached our middlemost value, which was 7, and then it started going down again in the same manner. So we get a probability distribution which looks very similar to our theoretic. Let's have a look at another example now. So what is the probability distribution of the number of coin flips until I get a tail? So what I'm going to do now is, for each trial, I'm going to take a coin and I'm going to keep flipping it until I get a tail, and then I'm going to stop. And I'm going to count how many flips I did. And that is my outcome, how many flips I did until I got a tail.
In this case, I have a sequence of events. I just don't know how long that sequence is going on for. And how have we dealt with sequences of events before? We've used tree diagrams. My first flip, I can either have a tails or I get a heads. If I get a tails, I stop. Brilliant. If I get a heads, I flip again, and I can either get a tails or a heads. Again, if I get a tails now, I stop, and if I get a head, I go again. And again. And so on. What are the probabilities associated with each of these branches? Well, a coin flip is 50-50. So the first time I'll get a tail with probability a half and a head with probability a half. The second time I'll get a tail with probability a half and a head with probability a half, and so on. Now let's think, what are my possible outcomes and the probability associated with that? Well, here, my outcome was I flipped it once before getting a tail. Here, my outcome was I flipped it twice before getting a tail. Here was 3 times, 4 times, and so on. What was the probability of reaching this end point of the tree diagram? So remember, to reach probability of an end diagram, we multiply along the branches. So here it's just a half. Here was the probability of me reaching this outcome, so I multiply along the branches, a half times a half. So that's actually a quarter, but I'm going to write it as a half times a half, which is a half squared. Here, where we've done a half times a half times a half, which is a half cubed, and you can see a pattern. And in fact, this pattern here goes on forever, and this is our probability mass function.
And this is what we have here. That is the PMF we just derived. Now, when we have a pattern like this, a set pattern for each outcome, we have a kind of relationship between the outcome and the probability, which we can denote mathematically. We tend to do that. So rather than write things out forever, we tend to write it out mathematically, which is, in this case, it was a half to the power of the outcome, or 1 over 2 to the power of the outcome. You'll notice here something we might not have seen before. We can have a random variable with an infinite amount of outcomes and an infinite amount of discrete outcomes. And think about what that PMF needs to be doing. Each probability in that PMF needs to be a value between 0 and 1, and that's what we've got here. And the sum of all those probabilities, so the probability of an outcome happening, must equal 1. So if we have an infinite amount of outcomes, we need to make sure that when we add all these up, we get 1. Is that happening in this case? We have some advanced maths to be able to show that that's the case, but I can show you instinctively why that is true.
So what were we doing? We were adding up a half plus a quarter plus an eighth plus a 16th and so on. We were adding up half the previous thing every time. So imagine we were doing that with whiteboards. We were adding half a whiteboard plus a quarter of a whiteboard and so on. Half a whiteboard plus a quarter of a whiteboard plus an eighth of the whiteboard plus a 16th of the whiteboard, a 32nd of the whiteboard, a 64th, and so on. I hope you can see from this that we will never add anything more than a full whiteboard. We will never add up things which come to more than 1. And because we're never adding more than what's left every time, we can keep doing this forever using this rule. And eventually, we will keep adding and adding smaller and smaller stuff until we reach very, 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 very close to 1. If we add an infinite amount of these, we will get a 1, which is the probability of the full sample space. So this is a valid PMF.
PMFs written like this are useful because we can calculate from them summary statistics. That is, we can start describing these probability distributions in the same language as we were talking about data. We can calculate the expected value. The expected value is analogous to the mean. And it actually means that if we sample this random variable lots of times and take a mean of all those outcomes, we would expect it to be the expected value. And the more trials we do, the closer and closer that will get to the expected value. The expected value is denoted with this chunky e with brackets around the variable x. Some people use not a chunky e, just a normal capital E, and some people use square brackets depending on background. And it's just useful for you to recognize all those different symbols. And our formula for the expected value is add up all the outcomes multiplied by the probability of having that outcome. So this only works with numerical data because we're adding up values multiplied by probabilities. And it only works with ratio and interval data because we are taking a sort of middle of that. We need a meaningful distance. We saw this probability distribution of the outcomes of rolling a die. Now what is the expected value of this?
The expected value of the variable x, where x is the outcome of rolling a die, is going to be add up each outcome multiplied by its probability. Now in this case, all the probabilities were equally likely, but we have the outcome 1 multiply the probability of having a 1, which is a sixth, add the outcome 2 multiplied by the probability of having a 2, which was a sixth, and so on. Let's do some fraction manipulation to add all those together. So we get an expected value of 7 over 2, or 3.5. Now, what was the shape of this data? The shape of this data was symmetrical, equally likely symmetrical. And we are saying the expected value here, which is analogous to the mean, is right in the middle, 3.5, right in the middle of those two middle values, which shows symmetrical data.
Another summary statistic we can get out of a PMF is the variance in measure of spread. And we denote this by VAR brackets the variable x. And analogous to variance when it comes to data, the variance of a random variable is the expected value of the squared difference between each outcome and the expected value. So it's the mean squared distance between each value and the mean. And so the formula for variance is exactly the same as the formula for expected value, but now instead of taking the expected value of the outcomes x, we're taking the expected value of the square of x minus the expected value. Using that same example, the probability distribution of the outcomes of a die, let's find the variance now.
Now what is the variance of x? So now we want to take the difference between the expected value, which was 7 over 2, and every value, square it, and multiply by the probability of that happening. So the outcome 1 minus 7 over 2 squared, multiplied by the probability of that happening, which was a sixth. Add the outcome 2 and the outcome 3, sorry, that was a 6. Okay, now let's manipulate the fractions to work that out. So the variance of rolling a die is 35 over 12, which is about 2.91666.
And now this is really cool. This means that just by knowing what could happen, before we've even rolled the die a lot of times to get all the data, we know some summary statistics about what that data is going to look like. We've got the expected values. We think the mean is going to be 3.5. And we've got the variance. We think the average distance from that mean is going to be about 2.9166. Another useful thing which will crop up again and again is the cumulative distribution function, or the CDF. And this is a function that gives the probability of the outcome being less than or equal to that value. So like the PMF gives the probability of getting a value, the CDF gives the probability of getting something less than or equal to that value. We've seen the PMF of rolling a die before, so our CDF, denoted by this, the probability that our variable x is less than or equal to a given value, would be, for 1 it's a sixth, for 2 it would be the outcomes 1 and 2, and they are mutually exclusive, they can't happen at the same time, so we can add the probabilities for 1 and the probability of 2, which is a sixth and a sixth, which gives us 2 sixths. The same with 3. The probability being less than or equal to 3 is the probability being 1, 2 or 3, so we add up all the probabilities. And we can see then that calculating a CDF is just summing up along that row, 1 sixth, 2 sixths, 3 sixths and so on. And the CDF, the highest value will always be 1, because the probability of getting the highest value or less will be 1. Immediately from having the CDF, we can find what the median is. Remember, the median is the value where 50% of the data lies under it. So here it's the value where the probability of getting it or less would be 50%, or a half. And in this case, the median is 3, because the probability of getting 3 or less is a half. Even for more complicated examples, like the sum of rolling 2 die, finding the CDF is quite simple, because we simply need to sum across the PMF. And we should always get a 1 at the last value.